Before we talk about how to understand the fundamental theorem of calculus using displacement and velocity, we need the physical significance of definite integrals. Suppose we are given the velocity function of a moving object over a time interval from A to B. We assume the velocity function is continuous on the time interval. We want to show the displacement over the time interval equals the definite integral of the velocity function on the time interval. Step 1. We divide the time interval from A to B into n subintervals of equal width. We use t0, t1, t2 up to tn to denote the partition points. I want to mention the two endpoints A and B are included in the partition points. T0 is A and Tn is B. The width of the subintervals is denoted using delta t. Step 2. In this step, we'll approximate the displacement over the time interval from A to B by the sum of approximations of displacements over the subtime intervals. The displacement over the time interval from A to B is evidently the sum of the displacements over the subtime intervals. If n is large, then the width of the subintervals are tiny. Since the velocity function is continuous, on each tiny subinterval, the velocity over each tiny subinterval does not change much. So we can use a constant velocity to approximate the velocity over each tiny subtime interval. We can use the velocity at any instance as the constant velocity. It's denoted by FTI star. So the displacement over the tiny subtime interval is approximated by the constant velocity f of ti star times delta t, the time elapsed. Hence, the displacement over the time interval from A to B is the total of all such approximations. It's a Riemann sum. So we can see the larger the value of n, the better the approximation. So the exact value can be computed using the limit of the Riemann sum as n approaches infinity, which is the definite integral of the velocity function from A to B. Now we are ready to interpret the fundamental theorem of calculus using displacement and velocity. For part 1, if we interpret f of t as the velocity function, then g of x is defined as the definite integral of the velocity function f of t from A to x. So we can treat g of x as a displacement function. Of course, the derivative of the displacement function is equal to the velocity function. That's the interpretation of part 1. For part 2, we also treat the integrand as the velocity function. If big F is an antiderivative of small f, then big F can be treated as a displacement function. Now, in the equation, the left-hand side is the displacement over the time interval from A to B. The right-hand side is the displacement at time B minus the displacement at time A. Of course, the difference is the displacement over the time interval from A to B. So the two sides of the equation represent the same quantity. This is how we interpret part 2.